So today I'm going to talk about towards data efficient deep reinforcement learning for robotics. My name is Ali Badirzadeh, and I'm currently a postdoctoral fellow at Stanford University. So let's start with like a very general formulation of the problem. We know it as reinforcement learning. Reinforcement learning problem typically consists of two main components, an agent and an environment. The agent actually perform actions that change the state of the environment, and the environment in return gives back states, denoted here as ST, and rewards, denoted by RT. The goal of the agent is actually to learn a policy. Here, the policy, I guess you should also see my mouse cursor, right?
Yes, I
Okay,
can
good.
confirm that. Yeah.
Perfect. The policy is typically parameterized by parameter theta, and it actually assign, in this particular example, assign a distribution over actions condition on the state of the system. Our goal here is to actually maximize a notion of reward function, a notion of accumulated reward function over time. And that's the way that we try to optimize the parameters of the policy. In this talk, I'm only talking about neural network policy. So whenever I'm talking about the parameters, I mean neural network weights and biases. Good. Let's just look into one example for robotic problems. Here, for example, we want to actually learn to shoot a hockey puck to a goal position using a robotic manipulator. For example, the states are, in this particular example, are the robot joint position and velocities, as an example. Beside that, we can also, we have to actually also provide the position of the puck on the top table. And this information can typically be provided by using, for example, camera images, or they can actually be provided as raw camera images itself. So you don't need to do any pre-processing or after processing to extract the information about the puck position from the images. Next is about actions. Here, we typically interested about raw motor outputs or low-level motor outputs at time t. So we have to basically find a sequence of motor actions. Here, our robot consists of 7 joints. Therefore, we have to decide about 7 values for 7 motors over, let's say, 2-3 seconds. So the actions can be actually a sequence of motor actions over time. And the rewards in this particular example is basically constructed based on the final position, because our goal is to basically shoot the puck to a target position. But I will come back to this later, because for robotic, things are a little bit more complicated than it sounds. Before I go into a robotic reinforcement learning, I would first like to give very short overview about deep reinforcement learning success in different benchmarks. The first one is Atari one. I'm hoping that most of you should be already familiar with this kind of stuff. So DeepMind in 2013 demonstrated that for the first time they showed that you can actually learn reinforcement learning policies that can play different kind of Atari games from raw images, and they can actually play. It's completely self-play, so the agent tries to play over and over, and without any human supervision, and based on trial and error, and using basic vanilla reinforcement learning algorithm, it can actually achieve human-level performance in playing different Atari games. That was actually one of the first breakthrough in deep reinforcement learning. Followed by that, we have AlphaGo or AlphaGo Zero from, again, DeepMind. There they show that they can actually beat world champions in the game of Go. Probably some of you already know the challenges of the game of Go, but anyway, I don't want to go into details, but that was also one of the greatest breakthroughs of deep reinforcement learning in solving one of the very challenging problem that people would have guessed that we could have probably solved them in 20 years, but anyway, that was achieved already in 2015. AlphaGo was initialized based on some human demonstration, but then later on they could show that they can learn a policy from scratch without any human intervention based on pure reinforcement learning. Another interesting success of deep reinforcement learning is the work done by OpenAI to play game of Dota 2. And this game is actually much more complicated than the Atari games, and they actually show that they can beat human champions in a game. And but based on self-play, the agent can actually learn more and more and improve its skills to play these kind of games over time. And also, there's been lots of things happening. For example, on OpenAI gym environments, there's been basically developed to benchmark different deep reinforcement learning algorithm for many different complicated locomotion tasks, consisting of many different degree of freedom. And that was also, one of the very hot topics in deep reinforcement learning, and different researchers shown that they can use actually the same kind of algorithm can be applied to many different type of problem domain and achieve a very successful result on those domains. Okay, but however, challenges for deep reinforcement learning for robotic is quite different. And most of the environment that I showed, you could actually leave the agent to interact with the environment for many hours and try. I mean, the agent is actually able to do whatever trial and error as it wants and actually improve its skills over and over by collecting more and more data. But these are not actually possible if you want to do reinforcement learning research on robotics. The first challenge and the most obvious one is safety. Let's come back to the original example of a robot tries to shoot a hockey puck. In this particular example, the robot is holding a hockey stick, and you can't actually let a robot like this to do whatever exploration or execute whatever motor actions as it wants. Basically, if you just leave the robot for even 10 seconds, it will destroy itself or the environment. It's quite dangerous. And then that's like the end of reinforcement learning for that robot. So first of all, then, most important thing here is that safety is a big issue when you want to apply reinforcement learning on robotics, which was not a problem for the other example, as I just mentioned. Another problem is actually data efficiency. We're talking about mechanical systems, and mechanical systems can suffer from wear and tear. And therefore, you can't actually let a robot to learn for a very long time. We are limited when we are working with real hardware. We're limited in the amount of data that is available to us. So we have to actually think about data efficiency. We have to develop methods that can learn from limited amount of data. Next is exploration. Previously, in previous examples, the agent was free to do whatever exploration, and hopefully, if you give it enough time, then the agent would be able to actually learn to explore. But here, let's say that we want to actually explore how to shoot the hockey puck, but most of the time, if you just try free motion, basically the puck even don't move. And as a result, it's actually going to be a bit quite challenging exploration problem. And another thing here is that, again, this exploration is very connected to the safety aspect as well. So you can't do exploration as you want. Next thing is about credit assignment problem. This is basically, this of course exists in all kind of sequential decision-making problems that are typically applied to. But I want to actually emphasize it here again, because part of my talk is going to be about credit assignment. And credit assignment is basically whenever you make a sequence of actions, let's say you perform a sequence of actions, and then at the end you will receive some rewards. But it's not really clear which action result in this outcome. You have done, let's say, many different motor outputs over time, and therefore connecting one of these actions to this high outcome is not a trivial problem. That's problem is typically known as credit assignment. Next is reward shaping. In most games, or for example, in Atari games, you will always have a nice score that is given to the agent whenever it does something meaningful. But typically, real world does not provide such rewards or scores to our agent, and we have to typically design a reward function ourselves. There are some challenges in designing the reward function. One of the challenges is that actually that you don't want to put a lot of engineering effort. One reason for using reinforcement learning in robotics is actually to make policy training more straightforward. You don't need to have engineers to develop a new policy or new skills, and you would like to actually let the end users, for example, to teach a robot to do interesting stuff. But if, for example, to design the reward here, if you need to track the POC position, or if you have to actually penalize the agent for doing things that are dangerous, or trying to actually provide lots of information for how the trajectory should look like, then this would require a lot of engineering effort. And beside that, this problem that I'm showing on the slide, shooting a hockey puck, we tried it first, and we came up with 25 different reward terms. One of the reward terms, for example, was to actually hit the puck by the hockey stick. That was one of the reward terms. The other reward term was about not colliding with itself. The other reward term was not to make a collision with the table. The other reward was to consume as little as possible energy. The other was there was like a distance from the tip of the hockey stick to the puck, so that we can actually go as close as possible. And we came up with 25 different reward terms, and at the end, still the agent was not able to solve the problem, even after providing lots of supervision to this problem. And finally, the last problem is generalization. You would like to have an agent that after some training can actually work in any environment. And most of this reinforcement learning solution for robotic problems, they actually don't generalize. So if you train it, for example, in one kitchen environment, you can't expect it to work immediately in another kitchen. So these are some of the challenges actually that are related to doing reinforcement learning for real robotic problems that don't typically exist for if you want, for example, to solve a game, to train an agent to solve a game.
So Ali, before you go for the next slide, because you asked to interview, there is two questions for you for this slide. So the first one is why not to use simulators for the safety and data problems. So has been asked by Muhammad Ali, and Amir Hossein also asked. Go for that one first, and then we can ask the second question.
Okay, regarding simulator, I'm going to actually talk about, it's in this slide. So today's talk is actually one part of my today's talk is about sim to real transfer learning and what are the challenges that we are facing and how to deal with them. So I'm going to talk about sim to real transfer learning. So yeah, go for the other question.
Sure. So the other question is that can we do exploration in simulation environments and use transfer learning to robust performance in fields like PCI to cope with costs and other problems you might have?
I'm not sure why BCI. Are you talking about brain-computer interface? What does BCI stand for you?
Not sure, honestly, me neither. But maybe the question is, can we do exploration and use transfer learning in different problems, and just train a pre-trained model maybe, and then go for that kind of.
As I said, I'm going to talk a little bit about how to do transfer learning from simulation to real world.
And BCI seems that it stands for brain-computer interfaces.
Okay, but then I don't see the relationship to reinforcement learning for robotics, unfortunately. I mean, of course, one of my main areas is BCI, and I do a lot of research for, and actually I have a research team working on BCI problems, but yeah, it's not very connected to what I'm talking now about.
Yeah, sure. Maybe, we can actually start with your, asking the question in the end, if you feel better on
Sure.
that way. Yeah.
But both are fine with me. If I want to answer questions, then I would like to actually take the entire hour and talk about and also answer questions whenever there are some questions. I think this can be good. And if I feel that I'm actually under time pressure, I can be a bit faster with questions.
Okay, sure. Yeah, perfect. Yeah, go ahead then.
Great. So for today's talk, I'm going to talk about two different concepts. One of them is basically how we can do reinforcement learning using generative models. And the second is about meta learning to transfer policies from simulation to real world or across different robotic platforms. So let's start this reinforcement learning using generative models. Before going into details, I need to just provide some very, very rough background about generative models. So what does generative models do for us? Let's say that this is our data set and we want to actually generate photorealistic images of humans. One way to do that is actually to run a latent variable of the data. And latent variable is typically used to capture some attributes of the data. So for example, here, age, gender, I don't know, different type of eyes, nose, etc., can be captured by our latent variable. And once we have, we can assign different attributes, different values to different attributes in the latent variable. We have our generative model that can actually generate different outputs. Here is images. How we can actually learn a generative model? So basically, we want to learn a model that would basically maximize the probability, the log likelihood of our data. How we do that? We typically do it through marginalizing over our latent variable. We can introduce actually a variational distribution. As you can see, it will cancel out because it's introduced in the denominator and the denominator. Do some little mass, we use Jensen's inequality, and then we get this term. How this term, that's actually the term that we got in the previous slide. Sorry if I'm a bit too fast here, because you're just trying to just give a very brief background about the concept. Okay, now we are actually able to, we basically try to maximize the log likelihood of data using variational lower bound. And this can translate to our basically high-level model in a way that basically we will have an encoder, which basically encodes our data into the latent space. That is actually that's taken care by the, sorry, that's taken care by the second term. And this is the encoder term, the Q here. That's the one encodes our data into latent distribution. And then we have a generative model, which given a value on the Z, we will basically try to restore the input at the output again. We typically try to actually go through an information bottleneck. So we typically have a low-dimensional representation, Z. And there's actually a regularization term, which is formed by the KL divergence, which is basically you impose that the distribution of data here should follow a normal distribution. This actually kind of generative model training is called variational autoencoder training, or VAE models. Another way to do generative model is through adversarial networks. That's by playing a min-max game. And basically, the basic idea is that we have a latent distribution, we sample from that, we generate something, and then these are the fake images generated by our network. We provide some real images, give it to a discriminator, and then the discriminator tries to actually discriminate them if they come from, if they are real images or fake images, and this information is back propagated to the generative model to actually update its parameters to generate things that can't be discriminated by the discriminator model. And the discriminators, of course, is again updated to actually be better at discriminating. So if you just these two things play with each other, at the end, it will have hopefully some outputs from the generative model that that looks quite realistic. Okay, this is like whenever I'm talking about generative models, this is the final product that I have in mind. So we have a latent variable z that we can actually change, and based on different values of the latent variable, we will create different type of images. So here I just try to plot just two of the dimension of the latent variable. As you can see, this one dimension and this the other dimension. And as you can see, by changing the values and keeping the others fixed, you can generate images that somehow are similar, but will be different in other attributes. So that's a very brief overview on generative models. But the next question is actually how we can use generative models for reinforcement learning to do more data efficient robotic reinforcement learning. So let me start this like a very general formulation of the problem and a little bit about the architecture of the network. Assume that we have a deep policy. And this deep policy basically assigns a distribution over motor trajectories. Here, our action is not only one-time step action, but the entire trajectory of motor action. So for example, if you want to throw an object, it's not only about the next time step, but it's a trajectory over, let's say, 3-4 seconds of motor actions that will result in the throw action. And the policy actually is conditioned on a state. Here, the state can be like a low-dimensional representation of a task, or it can be just a high-dimensional camera image. So I just call that initial observation. And in most cases, I mean images here can be given as the input to the policy. Okay, input is image observation to this policy, and the output is a trajectory over motor actions that will be executed on the robot. And then once this trajectory is executed on the robot, we will have environment that condition on the state, initial state of the system, and also the trajectories which are executed on the robot will give you a terminal reward. This is the general problem formulation. Again, similar to what we did with the generative models, we want to actually maximize the log likelihood of reward this time. We want to find the parameters of the policy, capital theta, such that the likelihood of receiving high rewards will be maximized. Here we can marginalize over trajectories, tau, because this is basically currently let's assume this is our latent variable, and basically we want to actually see what sort of trajectories will give what kind of rewards. So if you look closer into this expression, you will see that we have a probability over reward condition on the state and the trajectory, and then we will have a policy distribution of the policy on this trajectory condition on the state. Okay, we want to actually maximize this expression using theta, but there's some problems here. One of the big problems is that the trajectory itself is quite high dimensional, and it's intractable to actually compute this this integration. What we can do instead then? This is one way to actually fix this problem is to use a human demonstration or offline data. And we can collect this offline data for a robotic platform through, for example, tow operation, kinesthetic teaching, or using blind controllers. Next is to using this data, we want to learn a distribution. We want to use generative models to learn the distribution of data. And when I'm talking about distribution data, I mean from the state T and the action sequences that are generated or executed on the robot. We want to actually learn this probability distribution. And once we have the generative model, we would like to then learn the high-level policy that basically uses this generative model to solve different type of tasks. Let's have a look back at what we had before. So before we had like this deep policy here that was mapping observation to trajectory of motor actions. Now we can actually divide this deep policy into two terms. The first component is actually a generative model that conditional and latent variable. Remember that I used notation Z before to denote the latent variable, but here is alpha. But conditional alpha, this generative model is now able to generate a trajectory, a sequence over motor actions as the outputs. And then we will have another component, which is a sub-policy, and this sub-policy tries to assign distribution over the latent variable conditional over observation. So why it's important to do something like this, it's because of the fact that now our log likelihood that, well, before, if you remember, we integrate over all trajectories, but this time, instead of integrating over all trajectories, we can actually integrate over the values of the latent variable. And this latent variable is much lower dimension, so it can be like 2-3 dimension, while our original trajectories can be like, I don't know, some hundreds of dimension. Okay, so but how we do that? Then let's look back at this term. So before we had to basically find the probability of reward, conditional state, and trajectory. And now the trajectory is simply replaced by our generative model term, and then we condition it over the latent variable. Why this is interesting formulation? The first reason is that now we have to deal with low-dimensional action spaces. We don't need to work with high-dimensional trajectories anymore. Another interesting thing is that we don't have temporal complexity anymore. Before, we were basically having a sequence of motor actions, but now we're only working with a 2-3 dimensional or even 5-dimensional latent variable, so we don't have any temporal complexity anymore. It's safer and more efficient exploration now. Why is that? It's because, remember in the previous slide, we first collect some human demonstration, and then we use a generative model to learn the distribution of these data. And these data are safe to run on a robot because these are the data that are collected by a human user. So therefore, our generative model now actually only can produce trajectories that are safe to run on a robot. And it's more efficient exploration. Why is that? Is because that now the robot does not try to explore meaningless trajectories, and instead it only try to generate trajectories that are close to the human demonstration. So that's why we can more efficiently explore the action space. And of course, it provides us a very straightforward to exploit our prior knowledge whenever they exist. Okay, then the question is that how to train the deep policy now. There are two components, as I said before, generative model and the sub policy. Therefore, we have two set of parameters, the parameters for the generative model and the parameters for the sub policy. How do we train them? Let's start with the sub policy first. Similar to before, we can introduce a variational policy. Remember that before we introduced a variational distribution, this time we're introducing a variational policy. Here, we also introduce a notion of task state, Z. S refers to initial observation, which can be like camera images, but Z here is the state of the system. Let's say a position of the objects here are given as Z, but S contains like images of the objects. And variational policy can actually work on the initial state. That's a good trick because then we can actually learn the variational policy much more efficient compared to the perception network here. And if you're interested about how the variational policy differs from the deep policy, actually the variational policy will have information about the object for these tasks. The information, the position of the object is given because the object is held by the other arm of the robot. So therefore, we know the exact position of this. That's like the variational policy, but the actual policy does not need the information. You can, information about the object was, and it only look into the image of the object. Okay, I would like to do a little bit of math here, very similar to what we did before. We again introduced variational policy, added to this integration, and do a little bit of math. I don't want to go into details, but we could find again another lower bound here, very similar to what we did with the generator models. And now we would like to actually maximize the reward look likelihood iteratively in 2 steps by first maximizing the lower bound, by minimizing this guy, because this is a non-negative term. If you minimize this, use with respect to Q, since this guy is not dependent on Q, and the left-hand side is fixed, minimizing this guy will actually increase this guy. So the first step, we're maximizing the lower bound indirectly by minimizing the second term with respect to Q. There's variational distribution. And the second step, we're maximizing the lower bound directly. If you're interested, actually, you can look into the reference that I provided in the previous slide. But I'm not going to go into too much details of these derivation. But as before, a little bit of math here. Interesting here, and now I'm talking about the expectation step. Interesting thing here is that after a little bit of playing with different terms, you get 2 different terms for the expectation step. One of them is a reward-seeking objective, which says that try to find the parameters of the variational distribution Q such that you get better rewards. And the other term actually is a trust region term, which tell you that to stay as close as possible to the original deep policy. So the distribution that is assigned over alpha based on variational distribution should not differ too much from the deep policy. So that's the trust region term. So maximization step now will basically, after doing a little bit of math, it will result in a supervised learning objective, which basically says that in the maximization step, try to maximize the deep policy. Sorry, try to find the optimal parameters of theta of the deep policy, such that we are as close as possible to the distribution which was found by the variational policy in the previous step. Here's a very general overview to optimize the look likelihood of reward. We're basically iteratively alternating between 2 steps. In the expectation step, we optimize the variational policy based on 2 terms. One of the terms is actually trying to get better rewards while staying as close as possible to the deep policy. And in the maximization step, we're basically trying to update the policy by through supervised learning by making sure that the distribution given by the policy is as close as possible to the distribution found by the variational policy. Okay. So far, I have talked about how we can actually train this sub-policy. You may ask, okay, what about the generative model? The generative model can be trained, as I explained before, using VAEs or GAN models. It's exact same thing as I told before. So the question then is that, okay, where the data will come from? Data, as I said before, can come from teleoperation, kinesthetic teaching, or blind controllers. Here's an example of blind controllers. So it's quite actually not that difficult for an engineer to design how the trajectory should look like, but they don't know. I mean, there's no task assigned to it. Just it's like if you want to reach the different points on a tabletop, this is how the trajectory should look like. But indeed, there's no target. It actually tries to blindly produce some data that can be used for training of the generative model. Okay, then so far I've talked about how we can train the generative model, how we can train the sub-policy, but what about the perception? If you remember from the previous slides, I was just talking mostly about learning from a lower representation of tasks, which was like the position of different objects is provided to the learner, and then doing supervised learning to train the perception layers of the deep policy as well. But basically, this is not still very data efficient because uh, because it may not generalize well to unseen situation, and in order to actually improve the generalization on the perception side, on the vision part, you actually have to train for a very long time with many diverse data, which is not a good idea actually using real robot data. So here I'm just introducing one of our recent works, which was in ICRA 2020, for how to learn a generalizable perception module. So first, we basically learn a task in a very simple environment. You see that the background is white, the object of interest is black, so it gives the best contrast, and actually we can use our EM policy optimization as described before to learn different kind of skills. Here is like a picking task and also a throwing task. We don't have any visual plotter, and we only have one task object here in the scene. And to just remind you, this policy is trained by first training the generative model, and then learning the policy layers based on the expectation maximization algorithm that I explained. So that comes from this algorithm. Now, this is not a realistic scenario. We want to actually learn to adapt the policy such that it will also work in more realistic situation as well. So this is, for example, a little bit more realistic. We will have more background plotter. We have some extra objects in the scene that they're only distractors. And beside that, our object is not just a black object. It can be like, so different target objects that are, as I will show here in this video. So for example, we want to generalize to different type of target cops. And we want to do it in a zero shot, meaning that we don't want to train it anymore. So it should be like, based on this kind of learning, we would like to learn doing the task with many different target objects and not being distracted from the other clutter that exists in the scene. So how we can do that? Remember that in the E step, I just described that we're updating the variational policy. So the E step will be the same as before. We're not going to change it, make any changes in the E step. But in the M step, we're trying to update a little bit of this objective function. Before, what we had in the M step or the maximization step, it was only a supervised learning that tries to make the distribution of the deep policy as close as possible to the variational policy. That was the way that we did it before. But now we want to actually update this loss function a little bit by introducing an adversarial loss so that we can actually use some extra images. So these images are not, I mean, we don't need to actually use a robot to collect these images. So they're just random images generated basically only using a camera. You want to use these kind of extra images and also the images that the policy has been trained with, and basically improve the perception such that now the policy would generalize to something quite new. How we do that is actually, again, we're using adversarial training. Basically, what we do is that we will have a feature extraction component, which is denoted by F. And our idea is that features that comes from the images that were used for training the policy originally should not be distinguishable from the features that are coming from more realistic images. And we do that by adversarial training, so that you have a discriminator that tries to tell them apart if the features come from the realistic images. Let's call them offline data. If the features come from the offline data, or if the features come from the robot data. And remember that we are sharing these visual features, this network, the parameters of this network to process both of these images. So therefore, this is the way that we are training the feature extractor such that features are indistinguishable whether they come from the robot data or from the offline data. And in this way, we can, as I can show here, we can generalize with zero shot. And for this pick and place and task, and the other one was pouring task. For both of these tasks, we could actually achieve almost 95, 98% accuracy when we pick different success rates. Sorry, when we pick different objects like this. I would like to actually give a little bit more, present a little bit more videos for when you're using the ID that as I explained so far. So some of them are my older research and some of them are newer ones. In all these research, we're using generative models. And also we are training basically a policy based on the EM algorithm that I explained earlier. The good thing here is that we can immediately, after having the generative model trained, we can immediately run the generative model on a real robot or a simulated robot, and it will generate acceptable trajectories. And the great thing here is that, for example, for this throwing task on a peer-to robot, I only spent half an hour training the robot, so it was quite efficient, and it could actually all the trajectories which was generated by the generative model could be run on this robot without any problem. Okay, I want to actually very briefly, now that I have talked about the EM policy training, I want to actually very shortly, briefly talk about another research that came out of this formulation, and that's about multitask learning. So our goal is to basically learn here in this particular problem. Our goal is to basically learn a policy that would be able to navigate through such a complicated environment. And the agent actually have different strategies. It can lower the torso to move to pass above the some of the objects. It can actually higher its torso to go through the narrow passages, and some extra here. Yeah, exactly. Here are the kind of skills that I'm talking about. So it can actually move around them, go on top of them by increasing the torso height or by decreasing the torso height. These are the different kind of strategies we can implement by this. And again, here, we're going to use the exact same EM policy training, but this time, what we do differently is that in the EE step, we are, instead of having only one variational policy, we're creating 3 variational policy. Each of these variational policies are trained with to learn different kind of behavior. So as I said, these are some of the three examples about the type of behavior it can learn. And in the M step, we're trying to combine all these different skills to learn the deep policy. So, and this is the performance of the deep policy. And we did some brief comparison to the state-of-the-art method, which was PPO at that time, and we showed that our EM algorithm can actually improve the performance much better compared to PPO policy training. Okay, great. So far, I have talked a lot about how you can basically do generative model. You do reinforcement learning using generative models. But the next thing I want to talk a little bit more about is the advantage of meta learning for data efficient robot learning problems. The first thing I want to start with is the problem of sim to real transfer learning. So the question is that if you want to learn a policy on a real robot, it's going to take a lot of time. It would require a lot of robot data. It requires a human supervisor to actually reset the task and to run the experiment. So everything is going to be quite expensive to collect. The data is quite expensive when it comes to the real robots. But on the other hand, we can actually create very high quality simulation engines that can actually simulate most of the properties. So why not using simulators to learn a policy and then directly deploy them on a real robot. We have two options here. We can actually learn a general model, so that would basically work in simulation, and then it will, like in a zero shot, can be transferred to the real setting, or we can actually learn a learning agent in simulation, which can be in a few shot adapt to the real scenario. First of all, I'm gonna make the first thing is that the gap between simulation and the reality is quite high, so that unfortunately the first option seems not be very trivial. So in our research, we tried that, and we unfortunately could not learn a policy general enough that can adapt in a zero shot to the real setting. But the other option seems to be much more promising. So I'm now going to talk about learning a learning agent, or doing meta learning for sim to real transfer learning. I'm going to only talk about optimization-based meta learning algorithm. One of the famous algorithm here is called model-agnostic meta learning, or in short, MAML. I don't want to go into details of this algorithm, but basically it comes. I mean, the idea naturally comes from the way that you typically, for example, fine-tune parameters using gradient descent. So let's say that these are the pre-trained parameters denoted by theta. Then alpha is your learning rate. This is gradient of your loss function with respect to theta. And these are some training data for a new task. And basically, you can do fine-tuning to find the new parameters, let's call them phi, that would be suitable for a new task with the data DTR here. How we can actually improve the learning efficiency here? We have actually a number of options. One option is to find a good initialization over theta, such that after a few gradient descent, we can get the optimal values. We can actually play a little bit with the learning rate. We can come up with better loss functions, or we can try to find a set of more informative training data that facilitates learning or fine-tuning to a new task. MAML works actually based on the first ID. All these things, there are lots of different algorithms that actually deal with different options, but I'm going to talk about the first one, which is the MAML framework. And this slide is borrowed from Josephine. MAML, or model-agnostic meta learning, basically tries to find a good initialization such that after few gradient descent, you would get a good performance on any individual task. So the goal here with MAML meta learning is not to actually learn a policy for one task, but instead we're interested to learn an initialization that can adapt to many different tasks as easy as possible. Okay, now based on this explanation, now let's get back to our sim to real transfer learning problem. So in simulation, we can't perfectly match the physical parameters in simulation in the real world. But what we can do in simulation is that we can create a wide range of different parameters in simulation. This is actually called something called domain randomization. Here in this particular example, we can actually adjust the linear friction over X and Y axis, torsional friction, rotational friction, Poc mass, and initial Poc position. So we try to actually randomly change the parameters, the dynamical parameters of the simulator with the values in the range given by the minimum column and the maximum column. And therefore, now we create, let's say, thousands of simulation environments, each of which is different from the others, because now the parameters, the physical parameters of the simulation is different from the others. But the policy actually solves similar problem, but with different dynamics. So the interesting thing here is that if we are able to learn a diverse enough setting that can be created in simulation, hopefully now we can actually adapt to the real world much easier, because this time we're not actually learning one single model, but we're instead learning a learning model that would basically first be trained in simulation. And once it's learned how to learn, we're transferring this agent to the real world, and hopefully it has enough knowledge to learn in the real world as well. We're going to use MAML framework in this particular problem. And instead of learning one policy in simulation, we try to find an initialization or the policy parameters in simulation such that this initialization can be adapted to any of this simulator in few-shot learning. And our aim is that after we can actually learn this learning agent in simulation, we hopefully can now transfer it to the real world now, and our real world is of course having different parameters as well. So for example, the blue POC has different physical parameters compared to the red POC, for example. And now, since our meta learner has been trained enough in simulation to actually solve different physical properties, now that it's placed in the real world, it can also do this task in few shots. So this is one way that we can do few-shot adaptation from simulation to reality based on using a concept called meta-learning. Now I'm going to talk about the second topic that I wanted to cover for meta-learning, and that's about multi-robot reinforcement learning. As you can see, as I've so far talked about, we can actually do a lot of effort to learn one policy for one robotic platform. So for example, here it was from simulation to the reality, and here is like directly learned on a robot. It's again directly learned on a robot, but basically using some extra tricks by using offline data to improve the generalization. The problem here is that we are only unfortunately learning on one robotic platform, and the policy, for example, learned on this robot cannot be transferred to the other robot, and basically the entire policy is rendered useless if you want to apply to something to a new robotic platform. Our goal here is actually something like this. We want to learn a policy on one robot, but once the robot has learned how to do that, we want to be able to transfer the acquired knowledge or the acquired skill to another robot with a different morphology. So in this way, we can actually improve data efficiency and enable transfer learning across different robotic platforms. Before I can go into details, I need to talk a little bit about policy decomposition. How we can decompose a policy to actually enable this transfer learning possible, make this transfer learning possible. We can actually decompose a policy to task-specific and robot-specific components. Here's an example. Let's assume that we have two robots, robot 1 and robot 2, and two tasks, task 1 and task 2. So we would like to actually find an architecture that can decompose task-specific component from the robot-specific. Here's one example. So the task-specific component can be like the perception network that can look into the scene and find a good representation of the object in the scene. And then the robot module can actually be our generative models and some fully connected layers that basically would output the motor outputs. So at the train time, the idea is that we want to train different combination of tasks with different combination of robots. At the test time, we want to test them on a held out combination. So here, task 2 and robot 2 has never been seen during training. So we want to see how we can basically adapt to a novel configuration, never seen before. Okay, our goal is also to do similar kind of decomposition. So we want to basically decompose the deep policy into task specific and also robot specific.
So Ali, we do only have 5 minutes.
Okay. All right, I'll try and do my best. All right. Oh, I'm sorry. I thought I have time. Okay, I'm just made a mistake in my time. I'm
No
very
worries.
sorry for that.
Sure. No
Okay,
worries.
I'll try to be a bit faster to just finish this up. Here, instead of just learning different robot components for each individual robotic platform, our goal is to use meta-learning to actually learn some robot agnostic layers, which can be used by gradient descent to actually adapt it to a new model for a novel robot. So here is actually our meta learning framework. So we created in total 400 different robots in simulation by changing the parameters of different robotic manipulators. Here are Kinova, Yumi, Frank, and Baxter. Then we did the meta learning. This is our generative model formulation, as I described before. We trained 400 robots to actually learn the generative models. And then at the meta test time, we basically use gradient descent to update the initialization to the generative model suitable for a robot for a novel robot. I would skip these ones, but here I wanted to say that we need basically two different type of properties for our meta learning. One is the meta learning should be probabilistic. Why it's that? It's because of the fact that if we have, here we're talking about few shot adaptation, and given few shot data, basically the task can be ambiguous. Here's an example of ambiguous data. If you provided this data set and these are the positive samples and these are the negative samples, once you're given a new image like this, it's not really clear if that's positive or negative because some attributes of this belong to the positive class and some to the negative class. That's why we need sometimes a probabilistic meta learning. And another thing is conditional meta learning. Sometimes task data are coming from multimodal distribution. So here, for example, we have 3 different categories of task data. And for that, we need conditional meta learning. Here is one of our recent work with which we try to extend MAML into probabilistic and conditional meta learner, and then we applied this new framework, this meta learning framework, to solve our multitask robot learning. Here are some results showing that for reaching tasks, our algorithm has performed much better compared to any other meta learning algorithm that exists today. Okay, today I talked about reinforcement learning using generative models and also meta learning to transfer training policies. And I talked about sim-to-real transfer learning and also transfer learning across different robotic platforms. Thank you so much for listening.